I'm John DeGoes, and I want to thank you all for coming to my talk on ZIO schedule. I'm going to talk about that here in a second, but first I want to, well, thank Ryan and the whole crew at Signify for having me out here. It's really great to be here, and I would not be here without their help and their sponsorship, so thank you for Ryan and everyone else at Signify for doing that. Thank you to Lawrence for the warm-up, nice warm-up, I thought. Introduction to using types to help us write better code, and that's some of what I'm going to be talking about tonight is about as well. Thank you to all you attendees. As far as I know, London doesn't have an end. It just keeps on going on forever and ever and ever in all directions. But I know if it did have an end, Osterley would probably be somewhere out near the edge. So thank you for coming all the way out here to see the talks tonight, and I hope to stick around and enjoy some pizza and beer afterward. And then thanks again to Signify for hosting and for flying me all the way out here from Colorado in the United States. So I came out here for one reason, well, one primary reason, because I love your steak and ale pie. I had my first steak and ale pie 4 years ago, and I have not been able to get enough since. Seriously, I'm addicted to those things. And also not just that, but I have to remind you folks in Britain that the best beer in the world actually comes from Colorado. We have 350 breweries. And only one of them is Coors. The others are all way better than Coors. So please come on out there and try some of our beer or hike some of our mountains. Next year I co-organize an event called LambdaConf, which is a functional programming conference. It's in June 2019, so come on out, have some of our beers, go on some hikes, and say hello to our local group of functional programmers. The real reason I'm here actually is none of those things. It's actually to talk about functional programming. I'm a bit of a broken record. No matter what conference you stick me at or meetup, I'm always talking about functional programming. It's like I can't find anything else to talk about. And the details change, like the libraries I'm talking about and the concepts I'm talking about change, but at the end of the day, it's all functional programming. And I talk about functional programming because I'm a true believer. I really am. Functional programming helps me write cleaner software that I can understand the correctness of. It helps me be more confident when I go into a code base and make changes, knowing that the changes that I make are going to result in a well-specified, correct software application. It helps me solve very hard problems for the business with confidence that what I'm doing is correct in the small and will also be correct in the large as I compose my large program out of smaller pieces. And of course, it just helps me sleep better at night. I don't like the things I used to do when I was a Java programmer. I regret many of them. And when I'm doing pure FP and Scala, I just feel good about the stuff that I write. I feel like the pieces fit together and I'm making something that's high quality that I can be proud of. And that doesn't mean it's perfect, no code is ever perfect, and I'm always learning, like all of us are always learning. But it does mean I can feel good about the work that I do and have a vision for what improvement looks like going forward. But you don't need to be. So if you're not a functional programmer, that's fine, because tonight I'm going to do things a little bit differently. And in fact, you can even hate functional programming. So functional programming is just programming with functions. And functions are math functions, so they're total. You feed them an input and they'll always give you an output that has the specified type. And they're deterministic, so you feed them the same input and you'll get back the same output. And then they have no side effects. So the only effect that a function has is computing its return value. And I understand if you don't like programming with functions. After all, who doesn't like writing partial functions? You've gotten yourself into a big mess way down at the bottom of the code base and have no way out. So what do? Well, you hit the eject button, you throw an exception, and you let your mate clean up the mess. That's what you do. So partial functions can be fun. They can be nice escape hatches. Or determinism. Maybe you hate deterministic functions. You love the surprise that happens when you call a function with the same input and get back a different output. Makes testing more fun. fun adventures on call as well, I can expect. Or maybe you like code that has side effects. Maybe it's just too simple to look at a function's type and know what it does just by reading the type. Once you start throwing side effects in there, the type says nothing about what the function does. It becomes completely divorced from it. And so in order to understand what that function does, you can't just look at the type. You have to dig into its implementation and study every line of code in there. And then that calls other functions, so you have to do that recursively, and you spend a lot of your time studying code. And that can be more fun than writing code. So I understand if maybe you prefer functions with side effects. But all that aside, I'm not going to try to sell you on the benefits of building your programs from math functions. Instead, I'm going to try to give you a new tool today that you can use to solve business problems. And yes, it happens to be FP, but shh, I won't tell anyone if you don't. We're going to focus, though, on the business pane tonight and show how some of the tools in FP allow us really powerful solution to problems that we all face every day, every week of our programming careers. All right. And who knows, along the way, at some point during the night, you might even become a true believer too. It can happen. Let's hope. I'm going to talk about a library I contribute to called ZIO. ZIO is a library that helps you build business software, helps you solve hard problems in concurrency and asynchronicity. And we'll talk a little bit about that because ZIO schedule is a component of ZIO, and to understand schedule, you're going to need to know a little bit about ZIO itself. So we'll just spend a little bit of time talking about that. And then we'll move on to talking about retries. So what do we do in our applications when we're interacting with a third-party service that isn't reliable? And we might have to execute retry logic. And it might not be simple either. That retry logic can get quite complex, and it can vary depending on what system we're interacting with. How do we handle that? And also repetitions. What do we do when we're doing things like running reports, or we're sending notification emails to users, or other types of things that we want to do on a schedule? What are the tooling, what are the requirements of that domain, and what are the tooling that we can use to solve problems like that? And then I'm going to introduce the ZIO solution for these, which is ZIO schedule. And I'll show you how schedule has a few building blocks that you can use to assemble to solve any problem you can imagine in either developing retry strategies or repetition strategies. And these few building blocks, even though they're not very many, they compose, they snap together in all the right ways necessary to solve arbitrary problems. And that composability is a real asset for you as a programmer because it means you don't have to keep a massive, monstrous API in your head, one for doing retry and another massive, monstrous API in your head for doing repetitions, and then basically memorize which API method you need to use in all the different circumstances. You don't need to use that. You can take a few different building blocks, you can snap them together to solve the problem that you have. So what is ZIO? ZIO is a zero-dependency, small, very lightweight library that helps you build high-performance, type-safe, concurrent, and asynchronous applications. And these applications don't leak resources, including threads, but also things like sockets and file handles and database handles and so forth. And these applications are easy to reason about compositional. So you can reason about these applications in pieces, and if you have confidence of the correctness of the pieces, you can have confidence in the correctness of the whole. And they're easy to test and refactor. You can surf over to the Github website for that. It's Scala Z-ZIO on GitHub, and there's a microsite with the beginnings of good documentation. And PRs are accepted, but it actually has considerable documentation and full Scala docs for everything in there. So ZIO solves a fundamental problem, and what it does is the core abstraction of ZIO actually lets you take something that you take for granted and you use in your everyday life, and it turns it into a value. And that thing that you use in everyday life is basically a group of statements. So all your programs are collections of statements. And you can view your program is being composed of smaller programs, which themselves are composed of statements. So when I say program from now on, I want you to think in your head in terms of a bunch of statements. And the problem with statements, I mean, obviously we need to write statements in order to get stuff done, but the problem with statements is that when we use them to describe effects, that is, we use them to read from files and write to databases and call other APIs and so forth, that these statements are second class. That is, our programming language does not give us any ability to abstract over duplication that occurs in a statement context. And that's because statements aren't values, we can't pass them around. We cannot take a bunch of statements and pass them around to a function. We can't take a bunch of statements and stick them in a data structure. Statements are not values. They're something else. There's some other weird thing in the language. They're not values, but there's something else. And that something else are standard machinery by which we abstract, which is writing functions and using data structures and defining function combinators and so forth. The means by which we factor out duplication doesn't apply to this weird thing called a statement or a collection of statements. And so we can't pass statements to functions, we can't return statements from functions, we can't store statements in data structures. And obviously there's ordinary statements are always going to be synchronous. And if we want concurrency, we're going to have to do that manually via threading or actors or some other means of obtaining concurrency, because statements are just synchronous, single-threaded, one after another. And then finally, with statements, we have a limited form of resource safety called try finally. Try finally is great. This is how we make synchronous applications that don't leak resources. We open the resource in a try block, and then we close it in finally. And now we have a guarantee. If there's some exception thrown from there, or the thread was interrupted or killed or whatever, then the resource will be released in the finally block. But unfortunately, today's applications are mostly not synchronous. We stopped programming synchronous applications a few years back, and today's applications are largely asynchronous. And try finally doesn't work for asynchronous code. It only works for synchronous code. And it doesn't even work all that well for synchronous code, but at least it does work. So all these are problems that come from the fact that our programs are statements, and these statements are second class. They're not first class values. And so because they are second class and not first class values, there's a tremendous amount of power that you as a programmer don't have. Your power was stripped away from you. You can no longer do all the things that you love to do with expressions, like writing a function that does a bunch of common logic that you can reuse across your code base. You can't do that with statements. But there is a way to recapture that, and that's something called the first class effect. In this first class effect, you probably heard of it before. These things are called IO monads, task monads. Future is similar to one. It's not exactly one, but it's similar to one. So you probably use something like this at some point already in your Scala career. And what a true first class effect like ZIO's IO monad is it's a way to take that group of statements, that program, encoded by statements, and turn it into a first class value. And as a first class value, you now have all the same power that you have over expressions, you now get over programs. Because you can now pass your programs around to other functions, and you can return them from functions. So you can build program combinators that factor out duplication. You can store these programs in data structures. You can do all kinds of crazy stuff, and because fundamentally it's a value, we can bake in very powerful features like asynchronicity and concurrency, and make it very, very easy to use these features. And we can even bake in resource safety that works not just across synchronous code like try finally, but works across asynchronous code as well, and works in the exact same way, so you don't have to worry about it. So all of these are benefits that we gain when we take something that's not first class and we turn it into a value and we make it first class. And that's what IO is about. That's what ZIO's IO about, is turning your non-first class programs into first class values that you can manipulate as if they were any other value in your programming language. And this does require a paradigm shift. It requires you to totally rethink what an effect is. an effect becomes a value, actually, an immutable value. So your programs, instead of becoming collections of statements that do effects, instead, in ZIO, we model that as an immutable value that describes a sequential series of effects. So it's this, if you have an IO in your program, then you know that's an immutable value, and it's just a value, so it's merely describing an effectful program. That's all it's doing. It's a description of an effectful program represented as an immutable value. And that's a massive paradigm shift. It can take months to totally come around to that way of thinking about effects. When you're no longer doing stuff and you just have values that describe stuff to be done, that changes the way you write software. But it also turns your programs from collections of statements into first-class values that you can leverage all the machinery that you're already an expert at. In ZIO's case, there are two type parameters, E and A, and so this immutable value that describes an effectful program, this program can either fail with some value of type E, or it can return a value of type A after doing a bunch of stuff. It's like any other program. All programs in the world, they either fail, they throw an exception or something, or they compute some value, which might be unit. It's the same way for IO. IO is a model, an immutable value that models an effectful program that may either fail with an E, or ultimately at the end of the day, after doing a bunch of stuff, it can return an A. And that means we can, with ZIO's IO, we can describe the type of computations that can never fail. We simply use nothing for the first type parameter. Nothing in Scala is a type that has no values. There are no values of type nothing. That's why it's called nothing. It doesn't matter how hard you look for one, you're never going to find a value of type nothing. And as a result, the Scala's compiler knows this, it's baked into the Scala language. It treats nothing as a subtype of any other type. So you can use, if you have a nothing, you can treat that as any other type. And that's sound because there are no values of type nothing. Nothing is the uninhabited type. So whenever you see nothing in covariant position, like if you see a function that returns nothing, it means that it doesn't return because it could never return a value. If you had a function that threw nothing, you would know that it would never throw because there is nothing that it can throw. But nothing tells you some information, and in this case, when you stick it in this slot, this covariant slot of IO, it tells you you have a program that can never fail. If you stick it in the other slot, it tells you you have a program that can never return. And if you stick it in both slots, it tells you you have a program that can never fail or return. This is something that never goes down. It like catches its own exceptions and just keeps on going in a loop and never returns. It's like a server that's self-contained and catches all of its own exceptions in a loop. So let me talk to you real quick about some of the benefits of modeling effects as first-class values. First off, it gives us the ability to have a new concurrency model, one not based on operating system threads, but based on fibers. Fibers are green threads implemented in a library. And that's what ZIO has, is green threads implemented in a library. So what this gives you the ability to do is have as many threads as you want, virtually, with almost no cost. So in this example, I create 10,000 workers just by filling the list with this worker. And I'm demonstrating a couple of things here. First off, that these IO programs are nothing more than values. I have a program that's a value, I'm replicating it on a list 1,000 times, now I have 1,000 programs. I have 1,000 programs. This is power that you don't have when you're dealing with statements. You can't replicate statements, you can't do anything with statements because they're not first class. But when your programs become first class values, I can take and I can stuff 10,000 of these things in a list. And then I can call this other thing, we'll talk about it later, called fork all. It just forks them all off into independent fibers. And now I have, in theory, 10,000 fibers all running concurrently. Of course, these are lightweight threads, so they don't actually consume 10,000 threads. Because they're always asynchronous and there's no blocking code, 10,000 fibers can actually execute very efficiently on a small number of threads, say 4 threads. And in this particular example, there's a queue. There's one queue that takes stuff out forever, and then there's a bunch of stuff that there's 10,000 workers that stick things into the thread. So you're not going to consume an unbounded number of threads here. It's actually going to be bounded by the capacity of your single consumer thread. So the faster that guy is, the more actual operating system threads will be consumed. But most likely only a couple of threads will be necessary in order to satisfy the requirements of 10,000 fibers. And that gives you tremendous scalability. It gives you the capability to not even have to think about threads anymore. You can literally just spawn them up, without number, without limit, and not have to worry about them, which is a real benefit. Another benefit is that everything in ZIO is non-blocking, so everything is asynchronous, but it doesn't look like it's asynchronous. Just like if you've used future in a for comprehension, it looks like things are happening sequentially, and it almost looks like you're blocking, but you're really not blocking. And it's the same way in ZIO. Things may look like it's blocking if you use them in a for comprehension, but nothing ever blocks in ZIO. There's no way to make anything block. Everything is asynchronous. The queues are asynchronous. Everything else in ZIO is 100% asynchronous, which means everything returns instantly, which means minimal CPU work is being spent. There's no spinning that occurs. There's no blocking. There's none of that other stuff that just wastes operating system level threads. There's safe concurrency. So here's an example of a parallel for loop. It's called par traverse. This does a bunch of things in parallel. And it's safe, first off, because it's very high level. We don't have to think about threads. We just say we want to do all this stuff in parallel. So we aren't dealing with the unit of a thread. We don't have to worry about starting threads or cleaning them up, terminating them. Not only that, but the primitives built into ZIO are safe by default if you do a bunch of things in parallel and you need all their results. If one of them fails, then all the others will be terminated immediately and all their resources safely cleaned up. You don't have to even think about that. It just happens automatically. And that's something that you're going to see often in ZIO is things just work. And unnecessary computation is always terminated immediately and all the resources are cleaned up. And that happens whether you're racing a bunch of things together, a bunch of different computations in parallel, or whether you're doing a bunch of different computations in parallel. If you need the results of those and the results can't be satisfied due to a failure somewhere in that big old complex graph, then all the other computations that you didn't need will immediately be terminated and all the resources will be cleaned up. ZIO has baked in interruption, and that means you can write recursive code that looks like ordinary recursive code you would write using future or something. And that code can be interrupted instantaneously. There's nothing you have to do as a user to benefit from that. All the code you write using ZIO is interruptible at any point. And it's impossible to do this with future, and it's guaranteed to be resource safe when you do it with ZIO. And that's because of a primitive called bracket, which basically gives you try finally. It gives you try finally, but a version of try finally with better semantics that works across your synchronous code, but also your callbacks, asynchronous code, and also works in the presence of concurrency. So bracket is the try finally for the modern era. That makes sure that if you can acquire a resource, then that resource will definitely be released regardless of what happens to the fiber that's running that computation. Whether it errors out because it threw an exception, whether it's interrupted because it happened to lose a race or is one of 1,000 different parallel computations and all of them were needed, you don't have to worry about that. So long as you guard resource allocation using bracket, then you have a guarantee that your application cannot leak resources. And finally, because ZIO's I/O really is a model of an effectful program as a value, and because it's as a value, you can now write combinators that work over programs. You can write functions that take programs and return programs. It offers you a level of expressivity that you cannot obtain in procedural programming. You can't do it. There's no way. This is a web crawler in a single slide. And this will traverse a bunch of pages, extract out URLs, and do all this other stuff. It's massively parallel. So because it uses this par traverse thing, it's going to go out and just start exploring this in parallel up to the limit of the number of threads that are being backed by the runtime system. So this is a massively parallel web crawler in a single slide, whose types tell us a number of things about this property. For example, we know that processing a page can fail because we have this type called IOEA. We also know that the web crawler itself cannot fail because we've got nothing out here. And the compiler verifies that we are appropriately handling all our exceptions in the right places and doing something useful with them. So this is compile time guarantee that our web crawler cannot be taken down for any reason, but yet processors can fail on individual URLs and with specific web content. And then actually you can, if you look at the implementation or even just the types here, you can see that what's happening is it's accumulating errors in the results of processing these things. So that's what happened, is on a given page, it'll just pull out. If you run into errors on that page, it pulls them out and accumulates them for later. So this level of expressivity is something that you can't get from procedural programming because you don't have a way to write functions that work on statements and return other statements. It's just not possible. All right, so that's what I/O is, and that's I do that brief introduction just because you're going to see it in some of the other slides, and you're going to wonder, what's this I/O thing? I/O is just a program that's either going to fail or return a value. And what it is, it's an immutable value that describes an effect of the program. It doesn't actually do anything, but it's the analog of a first-class handle for a group of statements, but cleaned up and made faster and all that good stuff, stronger resource guarantees and concurrency with asynchronicity. So retries. Many times we're working on an application and we're interacting with a web API or database or something, and sometimes it fails. And sometimes it fails for reasons that will be resolved. For example, it could fall for any one of a number of client-side reasons. Maybe we're calling it too fast, for example. And we don't know that because we're just running on, we're a service on one node, and there may be many nodes on which our service is deployed. We can't actually know these things in advance. But we can know that there are many reasons that it can fail, which are transient. And also the server itself, whether it's internal or a third-party API, it could just be inaccessible right now from our point of view due to inability to route between them. Or it could be down due to maintenance. Or it could be their server got overloaded, or there are so many different reasons these things can fail, and our application has to deal with the fact that, hey, we need information back from this API we can't process. We can't make further progress inside our application unless we get the results back from this API. And we don't want to give up right away because many of these failures are transient. Like most times you interact with the database, if it doesn't succeed, there's a chance the database was just overloaded and you try again and maybe it'll work. But if you're too naive about that, of course, then really bad things can happen. You can actually cause problems that are non-recoverable. But generally, when we write our applications, we want to be resilient in the face of transient failure. Because if we are not, then we're going to give up when it would have succeeded otherwise, and that's going to lead to loss of customer orders or bad customer experience, or who knows what problems it's going to lead to downstream, but there will be many problems. And so as a result, we often have to bake retry logic into our application. It's not just for web APIs either, is it? It's virtually all over the stack, whether we're doing streaming computation or cloud storage, log file, like database, analytics, caches, local storage, and all these web APIs, and microservice architecture, RPC, and just on and on and on. All of these things can fail for transient reasons. And if we had only tried one more time or given it a little more time, maybe it would have worked, and oftentimes it does. So this is a fairly big problem. Unfortunately, it doesn't have a great solution. That is, when you're writing a naive attempt to solve something like this, you have your method here called network request, and I've made this synchronous just so it fits on a single slide. If this were asynchronous, with callbacks and all that other mess, then it wouldn't even fit on a single slide. But we have our method called network request, which is going to give us an A. And then we want to create a version of that that will repeat that if it fails. And even just doing a simple, okay, retry max number of times separated by milliseconds in length is rather verbose. And it's very specialized to the method that we're trying to make repeatable, the network request method. And also on top of that, it's synchronous, so it's going to suck up CPU cycles. It's going to hog up a system thread while it's waiting to do these retries. And it's totally inflexible. You can see if we changed our mind about how we should retry this network request, we have to change a lot of code, and we have to verify that our while loop and the algorithm, the logic inside here is still correct. And then if we want to scale this to some other method, you know, copy paste the code and go on. And that's what people do for a while, and that's why there are libraries like Quartz and Obsidian and whatnot to make these types of tasks easier, because they are very painful to do in the general case. Repetitions too. Many times in our applications there'll be something that we'll have to do after a certain amount of time. Like for example, at the end of the day, maybe we want to generate a report and send that to a manager or a customer account or whatever it is. And we might have to do that for every user. Not only that, but we might have to do it every single day. We might have to do it, we might have to do per user and also per account reports. And we might have to do those on different schedules, like per account reports every week, per user reports maybe every day. And then there might be pro user accounts and third-party accounts and all this other stuff. And reporting is just one of many different places in an application where we might have some sort of task that we want to repeat on a regular schedule until some result is obtained, or maybe indefinitely. Other examples include log rotation, file cleanup, in general, garbage collection, service heartbeat type applications where we have to keep on pulling something every once in a while and making sure it's up, or pulling back some reference data from it. Retrieving data, so like pulling stuff from FTP sites and remote sensors and all that other stuff that has to be done on a schedule. Doing user reminders based on activity, user notifications based on events they've done, all that requires scheduling. Uploading local data or snapshot data into data warehouses or Hadoop or third-party systems. And then all the garbage collection stuff, of which file cleanup is an instance. All these tasks are examples of things that we have to repeat on a regular cadence. If you want to do this naively, then you write code like this. You have your report gen function, and then maybe in this one, we just want to collect all these reports, and we want to do it up to some certain number, and then we'll go ahead and space them out by milliseconds long, and so we have our while loop and we sleep just like before. And several things should strike you when you look at this code. First off, this is monolithic, and it's very special purpose. And just like with the retries, if we change our mind about how this should be done, it's going to involve a lot of mucking around with the code. Also, this is not very abstract. This works for our report gen, but all this other stuff, it's going to have its own custom code in the application, and it's going to have all its same set of drawbacks. And then obviously it's not even practical because it's doing this synchronously, which isn't good. There's no error handling, error recovery. Who knows what's going to happen in the event of an error. But this is not how you should solve the problem, but it does demonstrate that fundamentally, if you try to solve these problems in a naive way, you're going to end up with lots of custom ad hoc code that has to be changed a lot, that's very monolithic in nature. And these are real problems. That's where there are libraries out there that can help you solve them. And ZIO's approach is based on a new data type called schedule, which abstracts over the notion of a schedule of events that occur separated from each other in time that may ultimately end. And the origin of schedule is that I've been working on ZIO for a little over a year, I think. And at some point, I started adding retry methods into I/O, because if you can have a program that does something, then you can write a combinator that returns another program that does that same thing, but if it fails, it'll do it again. So the fact that I/O values are first-class programs lets you write combinators to do retry in a way that you can't with statements. So you can just write this combinator that's going to retry like 10 times, for example. And so I did that. I wrote a combinator that it was called retry for. You gave it 10, and it would give you a new program that would do the first one up to 10 times until it succeeded. But then I needed another combinator because that didn't work in all cases. Sometimes I wanted to space the retries because it was unlikely if I tried 10 times in it right in a row that the problem responsible for the failure was going to be immediately resolved. Instead, I have to wait for maintenance to be performed or load to die down, the database to have some spare cycles to process my transaction. So I had to write another one that was like retry spaced or something. I can't even remember what it was. But basically it tried retrying only every so many milliseconds. And then that didn't work out so well in other cases because some classes of failures you can retry right away and they'll succeed. And other classes you can't. So then I needed an exponential combinator, like retry exponential. And I just saw the number of different methods were multiplying without bound. And that's because the number of ways that you can retry something or the number of ways that you can repeat something is without bound. You can't solve all problems in the world with a single method, otherwise you would have to have an infinite number of methods. And so I saw this anti-pattern creeping into ZIO. I thought, we're missing something. We're missing an abstraction here, a first-class data type that lets us say, this is what a schedule is. Because if we have a data type to represent a schedule, then we can have a hope of building combinators that allow us to combine schedules. And if we can build combinators that allow us to combine schedules, then in theory, we can have a small number of schedules that can be combined in an infinite number of ways. In other words, we can solve an infinite number of problems with a finite number of pieces. And that was the inspiration for schedule. And here it is. A schedule of AB is an immutable value that describes an effectful schedule which, after consuming an A, is going to produce a B, and it's either going to decide to halt the schedule, saying, I'm done, I do not want to continue, or it's going to decide to continue after some delay D. So that's what a schedule AB is. It consumes the A's, it produces B's, and then at every step, it has a decision to make. Am I going to continue? In which case, I might wait some delay D, like 100 milliseconds or something. Or maybe I won't wait, maybe I'll continue right away. Or I'm going to stop. Those are the things that a schedule can do. And it's represented here with this illustration. You feed in the A and it goes in, and then it looks at the A, presumably, and maybe it looks at other things too, like the current time or who knows what. And then it decides, should I continue or not? And if it continues with that delay, and otherwise it halts immediately. In other cases, it produces a B. And surprisingly, this is something I did not know initially. It's something I discovered by chance. After I had written this for retry, then suddenly I had a user request. They said, this looks great. Could you possibly consider doing the same for repeat? And I looked, and there was like 3 or 4 repeat combinators, because you can repeat for a fixed number of times, but you could also repeat for as long as some predicate is true and so forth, and those already existed. And I'm like, this looks awfully similar to the retry case. And then I went through and I started writing code for the repeat case, and then when I got done, I compared it with the retry case, and I was like, oh my goodness, this is almost the exact same code. And I was actually surprised by that. And now I'm not so surprised, because now I see them as flip sides of the same problem. When you're retrying, you want to know if you should repeat a program that failed with an E. When you're repeating, you want to know if you should repeat a program that returned an E. So it's the same concept, it's the same idea, only one looks at failures, the other looks at successes. And that's how schedule unifies across both retries and repeats. In the case of a retry, the schedule actually represents a retry policy that consumes errors of type E and then emits some value of type B, which could be useful when composing that policy with other policies. In the case of repeats, your schedule represents a repetition or recurrence policy. And it consumes values of type A, which are produced by the program that you're repeating. And it emits values of type B, which again could be used if you want to end that repetition at some point. If you want to terminate that repetition, then you can use that B, or it could also be used when composing that repeat policy with other repeat policies. So this single abstraction schedule allows you to build both very sophisticated retry strategies, but also very sophisticated repetition strategies. And the only difference is whether you're looking at errors or values, but that's just abstract type parameter. Like the code doesn't need to know that. The code doesn't need to care, and your building of schedules doesn't need to care for the most part, unless you need some information on those E's or A's. So let's look at some different schedules here. These are base schedules. Actually, there's only a few base schedules baked into ZIO, but then it has some other ones that are built on top of those. So I'm going to give you, not quite all of them, but almost all of them, just to get a sense for how rich this data structure is. Schedule never is the schedule that accepts any input and never recurs, so it never emits a value. And that's represented in the type. You can look at that and you can say this schedule never produces anything, because of course if you try to schedule something to run never, it's never going to run, therefore it's never going to produce any value. Schedule once accepts any input and then just produces a unit. No information, just does something one time. Schedule forever consumes any input and is going to recur forever without any kind of delay. So no delay, it's just going to continue again and again and again forever, emitting the number of recurrences so far. So it'll start out by 1, and then 2, then 3, then 4, then 5, then 6. And this B value, the output from the schedule, again, keep in mind you can use that when you're combining this with other schedules. Recurs is a schedule that just recurs the specified number of times. And then, like the preceding one, it emits the number of recurrences so far. Spaced spaces actions out by a specified duration. So it takes any input, doesn't care, and it emits the number of recurrences so far like the other ones. But the difference is here, not only is it deciding to recur forever, but it's adding a delay in between every step, adding the specified delay. So if you want to do something on a fixed schedule, like every hour, for example, then you use schedule.spaced. And note here that spacing occurs between the programs that you're running. Which means, if you have a program that runs for 2 hours and a delay of 1 minute, well, that doesn't really make a whole lot of sense, because your program's sucking up so much time and then you immediately run around and do it. It makes more sense for, like, if you're doing something every hour and your program's going to run really quickly. Schedule fixed actually overlaps the duration of the task. So if your task takes 30 seconds to run and you're doing it every minute, then it's only going to wait 30 seconds after the end of the task before it restarts it. So it does it on a fixed schedule. Exponential does just what you think. It starts from the starting duration and uses a scaling factor to basically, it's going to recur forever, but the delays that it produces at every step will grow exponentially based on the starting duration and the scaling factor. Conditional recurrences, this one is going to accept an A, and it's only going to recur for as long as that function returns true. So this is a do while loop. This is literally a do while loop. I'm going to keep on doing this for as long as my predicate function A decides to return true. And then do until, the inverse of that. You invert the predicate, you get do until. Collect. This schedule accepts any A and outputs a list That should be list of A, sorry. It outputs a list of A's. So it basically builds up a list of all the inputs it's seen so far. It's a schedule that collects its inputs. The identity schedule recurs forever without any delay and just emits its output. You feed it an A, you get back an A without any delay, and it always decides to continue. You can also, if you have an initial piece of state and a way to turn that state into another piece of state, you can produce the schedule by doing an operation called unfolding. So you start with an A, and then you unfold that to a new A by applying F, and then you apply F again to get a new A, and so forth. And so you get this schedule that takes any input and just produces this stream of A's. And this can be useful in some circumstances. And here's a schedule that recurs forever without delay, but just produces a fixed number, or a fixed value. Just you give it a fixed value, the schedule will always produce that value. It will always decide to continue without specifying any delay. You can also take a function f that goes from A to B and you can lift it up into a schedule. This schedule will recur forever without delay, and all it will do is take its input and feed it to the function, which will give it a B, and the schedule will output the B. And the API for using these is very simple. It consists of 3 methods, actually just one method. And then there are 2 simpler versions. The one method is very powerful and too complex, or too powerful for the general case. So instead there's 3 methods. For retry, 3 for repeat, and they look like this. You have your action, which is a program that can either fail with an E or produce an A. You have your policy, which in this case is a schedule that looks at E's, errors, and produces some type B. And then you take your program, action, and you call the retry method on it, specifying the policy. And that's it. And now you have a new program that will retry according to the specified policy. The one for repetition is exactly as simple, but a little bit different. Note here that the B from the schedule is ignored in this version because we retried it and ultimately we succeeded, so we didn't need the B. Whatever that schedule was producing, we didn't care about because the action succeeded. We get back an action of the same type that we fed as input. Repetition is a bit different. So in repetition, we call the action, we call repeat method on the action, specifying the policy, and we're going to get back the B, which is whatever was produced by the schedule. And that in general makes sense because when you're scheduling something to recur at a certain amount of time, every action is going to do something, and you either want to collect those things, or maybe you want to log them and return a unit, but your schedule of repetition when you're repeating these successful actions is going to in some way have to lose information, most likely, if this is going to be an ongoing thing. At the very least, it will consolidate that information because if you're repeating this action a bunch of times, it's producing a bunch of A's, you're going to want to do something with those A's, whether it's toss them in the garbage or whether it's write them out to disk or whether it's stuff them in a list. And the type signature here allows you to do that just by having a policy that can aggregate the inputs or whatever. The second one is retry or else, or repeat or else, and lets you specify what happens when things go wrong. So if you're retrying and you get to the very end and your policy says, no, I don't want to continue, I'm done, I give up, then what do? Well, you should at least know about that and have the ability to handle that by being given whatever the schedule was producing. So the schedule was producing a B, so your or else function can see that B and it can decide to do something, to make some recovery based on whatever that schedule was producing. And the same way, you could be repeating for some time. Maybe you're doing report generation, and so you have an indefinite schedule, just runs forever. Something goes wrong. Uh-oh, what do? You have to be able to have a backup strategy. So when something goes wrong, how do you want to handle it? And that's what the repeat or else combinator allows you to do for repeats. And then finally, there's the most powerful one, retry or else 0, repeat or else 0, which allows you to, your or else can produce a value of a different type entirely, So you get back an either out of calling those methods to indicate whether you succeeded in retrying or repeating, or whether you failed and you produce some other type of value. And that's basically the most powerful that you can ever use, and all the other two are just implemented in terms of the most powerful. That's the API. And really, honestly, in the common case, you're just going to use repeat or retry. You're going to be like action, repeat, policy. Action, retry, policy. And that's it. It's a one method API for retrying and repeating. Of course, what problems can it solve? If you looked at the list of combinators, you should be asking yourself, are there any actual problems that I can solve using these different base schedules? You've got the schedule that never does anything, the schedule that goes forever. I guess the exponential schedule could be interesting. The one that repeats for a fixed number of times, those could be interesting. But in general, our retry strategies are not going to be just this or just that. They're not going to repeat forever or never repeat. They're not going to be always 100 milliseconds till the end of time. They're going to be some much more complex strategy based on our knowledge of how interaction with that external service should be performed in the event of a transient failure. And how we solve those problems using the base cases that I've already introduced is by adding combinators. These combinators allow us to take schedules and combine them together to get other schedules. And if we have combinators with just the right properties, then in theory we should be able to solve an infinite number of problems with only a few combinators and a few base cases. When I first looked around for other ways of solving these problems as I was building out this library, I realized it's been done a lot of different ways. This is one example of doing it with futures. Futures, remember, are not values. If you have a future inside your code base, that computation is already running. So you can't actually build retry combinators for futures because they're already running. But you can like have a method that builds a future, and then you can add retry logic around that method. And that's what this example does, which is taken from a blog post. I did not write this. I wanted it to be as realistic as possible, so I just grabbed someone else's example. And what this does is it basically just wraps a method that creates a future in another method that calls that method a bunch of times, creating a bunch of futures, and embeds all this special case logic. And this is passable. It gets the job done, but it's not satisfying. It's complex logic. You have to repeat it every time. If you have different futures, you have to, copy this in different places, or at least create some sort of thunk over a future or whatever in order to abstract out that part of it. It's not very pleasant. And there's no obvious way. You can have lots of methods that look like this, and you would not be able to combine them in any sensible way. This is not a composable basis for retrying. And then the FP libraries out there, they do some other things. Some of them are interesting. Like FS2 has this interesting way of viewing a repeated action or a retried action as basically a stream of failures. And that opens up the door to some interesting possibilities, because if you have a stream of failures or successes, then you can do stream-like actions like dropping failures until you get a success, and then you can return that. So that's interesting. But you still, the logic for, okay, how am I going to execute this retry, still ends up being hard-coded. This is a kitchen sink method here that says, well, we've thought up a lot of common cases, and we're going to bake them into this method that has lots of parameters, and you just stuff in all these different things into this parameter, and if we've thought about your use case well enough, then we'll be able to support it by plugging in the appropriate choices. Otherwise, you're out of luck and you have to write your own. And this is, by the way, for a kitchen sink method, this is actually a reasonable method, because it has your starting delay, it has a function that can change that delay at some point, and then it has a max attempts, and then it has a filter on the type of exception. So if you want a kitchen sink method, this is not a bad idea. But there are lots of things that cannot be described like this. that are just beyond its scope, and you're on your own if you want something like that. And then Monix has some stuff too, but it's basically, retry for a fixed number, or retry while the throwable matches some sort of predicate, one or the other. Pick which one you want. And then there's an unfold one. And then the repetition is just restart this until specified predicate is satisfied. That's it. So there wasn't really a lot out there. So in Schedule, I had to look to functional programming, and it turns out that when you build a schedule with these types, there's a way to make it a monoid, which is a thing in functional programming that allows you to combine two things, and there's an empty. But not only is it a monoid, but it's also an applicative. Applicatives allow you to take two f's and combine them together into the same f. Like applicative parser combinators, for example, allow you to take two parsers and combine them into one. The applicative composition here lets you take two schedules and combine them into one, doing something with the values from both. It also turns out to be a category, because you have identity arrows and ways of composing these arrows. It's also a ProFunctor, in fact. It's a strong ProFunctor, it's a choice ProFunctor, and it's even other things. So it turns out that this simple definition of schedule from A to B has a huge amount of structure that I didn't have to invent. I could just look out there and say, hey, this is standard stuff in functional programming. All I had to do was write the methods. And what this rich language of composition allows you to do is, using a small number of combinators and a small number of primitives, solve any possible problem. So let's take a quick look at what these things are. The intersection operator. So the intersection operator takes two schedules and intersects them. What does that mean? Well, if I have one schedule S1, another one S2, then the intersection of those two is a new schedule, such that if both of these schedules want to continue, then the composite schedule will continue. But if either one says it doesn't want to continue, or both, then the composite one is not going to want to continue. Also, if both of them say to continue, but this one says 5 seconds and this one says 1 second, the longer of the two will be chosen. So that's what intersection is. And that satisfies all sorts of nice, wonderful laws. Union is the dual of that. So union of one schedule and another schedule will continue as long as one of them wants to continue. So as long as one of these schedules wants to continue, the union of them will want to continue. It's only in the case that both of them say, no, I don't want to continue, that the composite will say, I don't want to continue. And also, if this one says, I want to wait 5 seconds, and this one says, I want to wait 10 seconds, it's only going to wait 5 seconds. It chooses the minimum of the delay produced by the schedules. Sequence does this schedule and runs it to completion until it stops, and then switches over to this other schedule and runs that to completion until it stops. So it does one schedule and then it does another schedule in that order. And it produces, that should be either, and I don't know why that's too boring. It should be either of here. So you'll either produce the result of the first schedule or the result of the second schedule, depending on where it is inside the progress of that. Compose lets you take a schedule A to B and a schedule A to C and compose them together into a schedule A to C. So if you can go from A to B and you can go from B to C, you can go from A to C. Jitter is a combinator that takes one schedule and returns another schedule of the same type, except the delays from that schedule have been randomly jittered. This turns out to be a useful thing to do in distributed systems, to add random delays to your delays, just so you don't end up accidentally synchronizing and taking something down by accident, because a whole bunch of things you try at the exact same time. Collecting is a combinator that, when called on a schedule, produces a new schedule that collects the outputs of the first one. And then there's filtering, so you can call while input to produce a schedule that will continue for as long as the input is true and until. And then there's the output versions of those, so you can produce schedules that continue for as long as the output satisfies the specified predicate. And then given a schedule of A to B, if you can map the B to a C, then you can turn that into a schedule of A to C. And then here, if you're familiar with applicative, then you've probably seen these operators, left and right apply. And what they do is they do intersection on the schedules, and then they map over them, throwing away one side or the other. So they have the effect of both schedules, but they throw away one value on one side or the other, depending on which operator you call. And here's one that just logs the inputs. And of course, you can log the outputs as well. Just another one for that. All these different combinators are actually built in terms of, I think, 4 different other ones. So with 4 combinators, you can build even more combinators. And of course, with these combinators, they're sufficiently rich that you can solve real-world problems with them. Here's the logging outputs. Okay. So let's see if we can actually solve a somewhat realistic example using the base cases and the combinators. And this is how we'll wrap up. We'll wrap it up by this basically proof of composability. We're going to take the combinators, we're going to take the base cases, and we're going to see if we can solve an arbitrary made-up problem that happens to be somewhat realistic and also non-trivial. This is the challenge. We want to, let's say we're hitting a web API. We know it goes down sometimes, and when it goes down, we don't want to overload it. But also sometimes it's going to go down for a long time, so we eventually want to give up. And we'll just, cancel the end user request. We'll propagate that failure up to the top level in the event that happens. Here's what we want to do. We want to produce a jittered schedule that's first going to do exponential spacing, because that's a very good strategy to start off with. Try really fast right away and then back off if that doesn't work. You don't want to overload it, but also you want to account for the possibility of flukes. So do exponential spacing starting from 10 milliseconds. And then eventually the problem with exponential is, you'll go from 100 seconds and then 200 seconds, 400, 800, and eventually you're never going to be retarded. Like you're just outliving the life cycle of your application or the end user request. So at some point it just becomes impractical to keep on retrying at these ever-growing scales. So what we want to do is, after the spacing between retries hits 60 seconds, we want to switch over to fixed spacing of 60 seconds between recurrences. So 60 is going to be our cap. We're going to do exponential until we hit 60, and we're going to run with that cap. But we don't want to run forever. We're going to cap that to, after we hit 60 seconds fixed spacing, we only want to do that for up to 100 times. So we'll try for up to 100 minutes, and after that, we're done. And by the way, we also want to emit a list of the collected inputs. We want to collect these errors because we're going to log them. Or if we're not doing errors, if we're doing a repetition, then we want to collect the output of this task so we can do further processing on that. Or maybe just log it, who knows. So how do we do this? Well, you break this down into pieces and you solve it compositionally. So one piece that seems clear is, well, first off, can you imagine writing a solution to this problem using scheduled executor? Or using the actor timing system? Or using something like that? This is not going to be fun code to write. You probably will have lots of bugs. And if some business person ever decides you need to change the logic of that, then it's just going to be a world of pain. You're basically back from square one, because the kind of code that you need in order to write something like this using scheduled executor is low level and painful and really hard to get right. And it's hard to understand it once you come back to that kind of code. So this is the part that seems clear though. So you start with this. If the API is compositional, then you just look for little tiny pieces and you solve those tiny pieces, and then you can slowly sort of back your way out into the solution for the full problem. You don't need to worry about all that complexity right away. You can really work from those small pieces. So you see exponential spacing starting from 10 milliseconds, so that's exactly where we start. Exponential starting from 10 milliseconds. And then after, we have to do something else. But something else, it's not so obvious how to do that, so we'll just put question marks. So we want to do one thing, and then after that, we want to do another. That's the overall structure of the schedule, as implied by English. We only want to do the exponential schedule for as long as the spacing between steps is less than 60 seconds. So we need to filter that schedule by calling the while output combinator. And remember, the exponential schedule returns the spacing between steps. So we simply call dot while output, and we'll filter it to cases where the duration is less than 60 seconds. So we'll produce a new schedule that will terminate as soon as the spacing exceeds or is equal to 60 seconds. And then what about that question mark, question mark, question mark? Well, we know we want to do fixed spacing of 60 seconds, so we can add that in there. So we want to space these out 60 seconds. But we'll only do that for up to 100 times. So we've got to limit this. The fixed 60 will just repeat forever. So we've got to limit that for up to 100 times. So there's a combinator we can use to do that, and it's the intersect combinator. So we use the intersect combinator on the fixed spacing of 60 seconds with the recurs of 100. So we're taking two schedules. One of them wants to recur 100 times. The other one wants to recur forever, but it's going to space them 60 seconds apart. Remember how intersect works. It will continue for as long as both of them want to continue, which means as soon as recurs says no, then the combined composite schedule will also say no. And also remember that when we do and, it chooses the greater of the two delays. So fixed produces a 60-second delay, roughly, minus the length of the task execution. And recurs, it wants to go right away. It doesn't wait around. So the longer of the two will always be the fixed 60 seconds. So this will allow us to achieve a composite schedule that, for up to 100 times in a row, repeats with fixed spacing of 60 seconds in between. And then there's the whole jittered part that we're missing. So this is just a deterministic schedule. We need to add some randomness here, so we can avoid accidental synchronicity. So we call dot jittered on the whole thing to jitter the output of this. And then we only have one more thing to do. We need to emit a list of the collected inputs. Well, keep in mind, all of these schedules here are looking at stuff and producing output. And the type of the output is actually, it's either duration, tuple, int, I think, based on all the different pieces that we fed into it. We don't need that. We can throw it away. What we want is we want to collect a list of inputs, so we need to build a new schedule that collects the list of inputs. And then we want to do that schedule and this other thing, and we want to throw away the value from the left-hand side. So we're going to use the whole right apply thing that I showed you at the very end, which may seem strange, but after you start programming with implicative functors for a while, eventually you become very familiar with what those operators do. So we do both of them, or another way you could do that, by the way, is to do intersect and then map over the tuple, throwing away the left-hand side and keeping the right-hand side. It's the same thing. So we do right apply with schedule.identity. So identity just takes the A and returns it. And collect collects the output. So if we call schedule identity collect, we've got a schedule from A to a list of A's, so we're collecting the inputs. And then we take and we do that at the same time we do the other schedule, but we throw away the return value on the left-hand side to yield the list of collected inputs. And this is the total schedule. It actually consumes fewer characters than the English description. And of course, being code, it's much more precise. And also, it's testable. This is functional programming, remember. We can call run on this thing, and we can give it a list of inputs, and it will give us the list of outputs along with durations that it would have waited. So this is the power of composability. It's the ability to take a small number of building blocks and use them to solve any problem, even problems we can't even anticipate having now, and do it in a maintainable way. This type of code is maintainable. you can go in here and you can make changes. You don't have to decipher anything. It's all asynchronous, it's non-blocking, it's resource safe, has all the other great properties that ZIO has, and you can come back 6 months or a year from now, you can look at this and you can safely make changes without having to implement any logic yourself. The building blocks are there. Your job is to snap them together in a type-safe way that allows you to solve the problem at hand. So if you want to learn more, I encourage you to hop over to GitHub. There's the microsite, there's a Gitter chat room that I'm on occasionally, and other ZIO contributors are on there. And then there's Scala's Ed chat room too, which also has a bigger crowd, but it's beyond just ZIO at that point. It's also Scala's Ed. And if you like the feel of this, the feel of snapping together complex solutions out of simple pieces that have the right shape, then you might enjoy some of the functional programming training I do. I cover things like applicatives and monads, functors, higher kind of types, all that stuff. I even cover ZIO and schedule and many other things. And I'm doing it one in London, thanks to Signify. They put together this training. I'm doing that Sunday, Monday, Tuesday, and then I'll probably be back in December to do another one around Scala Exchange. And then there's one in Paris and Silicon Valley if you happen to be out there. So that's all I have for you. Thank you for coming up to or showing up to this meeting, and I hope you stick around for pizza and beer afterward.